Hello and welcome to this video on how sugars get named. This might seem odd if you're not aware of the diverse sugars out there. You might think sugar is just the white powder you put in coffee. As has been described in other What is Sugar videos, there is a wide range of sugars depending on how complex they are. This simple distinction creates two types, complex and simple. You could look at whether or not it is a mono, di, or polysaccharide. Even that is less than precise. You could look at the names for specific sugars. That can become an unwieldy system. This is why conventions exist for naming sugars, an example of which is called the IUPAC nomenclature. But these systems are also highly specialized, with only a few surviving in the common usage from each attempt. Let's take a look at both the specialized naming used for carbohydrates and efforts to create a standard system for names. The first of these is more accurately part of the specialized naming system, as it uses the number of units in the structure. This creates your mono, di, and polysaccharides. A monosaccharide example is glucose, a disaccharide is maltose, and a polysaccharide is starch. It describes complexity of the whole molecule, but is a very simple distinction that does not allow for the greater complexity of everything else that could be going on with each individual molecule or chain of molecules. This is why there is further subdivision of monosaccharides into those with aldehydes or ketone groups. This is where special naming begins. The position and structure of these is how each is distinguished, as the formula is the same for most sugars across the board. These two features are a major contributor to names. The presence of aldehydes creates aldoses, which are a form of reducing sugar, an example of which is glycosyl. These generally end with a ulose. Ketose sugars have a carbonyl and are the alternative to this. They readily absorb, and a common example is fructose. They also tend to end in a ulose name. You can also apply more direct measures like the beta and alpha prefixes that describe the location of the anoremic carbon. Alpha and beta glucose is a good example of this, and the difference has been described previously. Another distinction that is applied in a similar way is the D and L orientation of the sugar molecules. This is a measure of chirality, which will be explained in another video. It can be very simply described as the side of the sugar that one of the carbons that is special sits on, and is used as a reference for every other carbon. These two aspects are part of the standard naming scheme, and even sugars with legacy or long-used names have these applied. Another is based on the open chain approach to depicting saccharides. This shows a linear carbon backbone, and the active group or hydrogens branch from this. This is the simplest way to depict the carbohydrates, as it removes all of the orientation problems. The product is often described as a parent monosaccharide and contributes to the names of other saccharides. The carbons often start being counted from the aldehyde or ketone group. As with most of science, there are always exceptions to the rules. This is different from other ways used to represent molecules. It does not alter the molecule, it is just a different way of showing it. In the case of individual molecules, it can be, and generally is, easier to depict them this way. It does make it harder to grasp how the 3D depiction of the structure is when you show it as a simple two-dimensional representation. Here is glucose in a linear format, a projection format, and a model. As you can see, the ring structure for the purposes of depicting a molecule is easier when you are trying to understand what it does and how it works. But for chemical formulas, the linear measure is a little more practical. For what are considered short saccharides, which have up to 6 carbons, the common names are more regularly used. This is as simple as a 3-carbon sugar called glyceraldehyde, all the way up to the more relevant 6-carbon glucose. Longer saccharides are a bit more difficult. Systematic names can be formed from a stem or parent molecule name, and a prefix or prefixes. The stem names for the aldoses, with 3 to 10 carbon atoms, are triose, tetrose, pentose, all the way up to decose. The chain is named with the specific OSE nomenclature, so you know it is a sugar structure, and the number as a prefix. This is one of the successful naming standards, as it is both simple and practical. These can be displayed as a chain or linear depiction for ease of access or other practical reasons. When you are looking at a more realistic depiction, you may see it as a ring. The most common sugar rings have 5 carbons. These are called furanoses. There are many that have 6 carbons and are called pyranoses. A 3-carbon ring is a triose. These rings can vary in size and go from 3 to 7 or more carbons. The more common and stable forms are under 7 carbons and form a ring, which is why they are commonly shown this way. If you are slightly familiar with DNA, then you would know sugars make up the backbone of DNA with a special sugar called deoxy-ribose. It is special because of that prefix, deoxy, which indicates an alcoholic hydroxy group has been replaced by a hydrogen ion. This is also one reason for DNA methylation. Being a carbon ring, it is surprisingly stable, an important attribute for a structural part of something as essential for life as DNA. This is ribose, and this is deoxy-ribose, for the purposes of seeing the difference. It's small but important. Sugars that have an amino acid substitute for a hydrogen, like in the Maillard reaction, are unimaginatively called amino sugars. Further changes in the sugar can lead to these compounds being called glycosyl amines. A simple example of glycosyl amines is galactosamine, and an amino sugar is N-acetyl-D-glucosamine. The N of this group is the amino acid component. When linked with other sugar molecules of the same sort, it forms peptidoglycan, the material that makes up bacterial cell walls. Glycosides are mixed sugars bound together by removing a hydrogen. This leads to a hydrogen bond. It also produces water. They are formed when a monosaccharide reacts with alcohol in the presence of an acid. This acts as a catalyst. The sugar OSE suffix of the name is replaced by the OSIDE or oside suffix. The alcohol group name is put at the start of it. An example of this frequently occurs in flowers and dyes. A common example used in medicine is streptomycin, an antibiotic. To give some idea of how irregular the system of naming is, here is a table of the structures and names given for each sugar mentioned, and one where this naming structure becomes important for novel or very specialized sugars that are used in research. There is some consistency in prefixes, especially those that describe definite physical differences like orientation. Others are used as an adjunct or pseudo-prefix that tells you what the thing is like, such as the OSE component added to existing terms. There is a link at the top of the description with a far more complete summary of both carbohydrate chemistry and naming, some of which extends beyond the scope of the What is Sugar series. In reality, there is no universal naming scheme, and efforts to date have failed. There are a range of standards or best practice approaches for this, if you are going to be working with sugars on a regular basis. It is generally easier to memorize names and structures rather than understand the naming process in its entirety. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions below.